Hello everyone, we continue by solving together the example number 1, for which a tension test of a steel alloy results in the stress strain diagram shown in figure 318. Calculate the modulus of elasticity and the yield strength based on 0.2% offset. Identify on the graph the ultimate stress and the fracture stress. Here the curve is drawn, represents 0, A dash and B and C, and is taking from point 0 to A and magnifying together with A dash. For the modulus of elasticity, or what is called Young modulus of elasticity, the slope of this line is equal to the vertical ordinate divided by the horizontal ordinate. The ordinate of A is 50 ksi, this is the stress and this is the strain, and the horizontal distance until point A is equal to the 0.0016. So the modulus of elasticity is equal to the slope, which is 50 ksi. We multiply by 50 by 1000 divided by 0.0016. We'll find that the Young's modulus is 31.25 multiplied by 10 to the power of 6 psi. While the yield stress, the point of the yield stress is here is not clear. That's why he is making another line which is parallel to the Young's modulus, but starting from the specified point. In this example, he is specifying that he needs point based on 0.2%, which is 0.002. So he will move until he is getting the point 0.0020. Then he will draw another line for which the slope is equal to the Young's modulus until he hit the curve at point A dash. Then he come back and he will find out what is the vertical coordinate. You will find that the sigma yield stress is 68 ksi. So the yield stress at 0.002 will be equal to the 60 ksi. About the ultimate stress is represented by point B, for which the ordinate is 108 ksi, while the fracture stress is represented by point C, for which the ordinate is equal to 90 ksi. So here the fracture stress is 90 ksi. There is a new topic which is the thermal strain. When a bar of length L is exposed to the change of temperature, due to the change of temperature delta T, the bar length will expand by amount of delta T expansion due to temperature. This is called elongation due to the change of temperature delta T. The original length was L. The bar will get expanded, and here the gain of length will be attained due to high temperature. But if the temperature is decreased, then shortage of the rebar we will get. Delta T is equal to the alpha, which is the coefficient of thermal expansion. It's by degree centigrade, or 1 per degree Fahrenheit based on the units we are using. Between brackets we have the change of temperature expression, and L is the original length of the bar. If we divide the elongation by the length, we get another expression, which is epsilon strain is equal to the alpha multiplied in the change of temperature. There is also volumetric coefficient of thermal expansion. When there is a cube, all the sides equal to L naught, and it's exposed to temperature, and the length of each side increased and becoming L. So the volume here as a result of the thermal expansion will be increased and becoming V, while the original volume was V naught. So the increase is represented the increasing coefficient, or coefficient of proportionality. E can be evaluated as the final volume minus the initial volume divided by the initial volume. Here there is a table of the thermal expansion coefficient at 20 centigrade. Here starting from glass, ending with silver, and these are the fractional expansion per degree centigrade multiplied by 10 to the power of minus 6, and here the corresponding Fahrenheit multiplied by 10 of the power of minus 6. Thanks a lot. We'll continue next time. See you and goodbye.